Welcome to the video tutorial for 9.3.4 Thin Film Interference. We've got 3 learning objectives today, so let's get right into it. Our first learning objective is to account for the colored appearance of thin film. In other words, why does thin film have this rainbow color that we can see down here? So the reason for that in really short terms is it's because of double interference. That's really hard to talk and write at the same time. Because of double reflection, okay, or interference in general. So it's actually the double reflection that causes interference. So typically what happens is that, let's say you've got the sun over here and it's giving off white light. So when white light is incident on a surface, it's going to reflect some of that light. And when it reflects light, because we've got quite a few different layers here, I'm going to use a slightly different color. So let's say there's red light coming in. It's going to go through the medium. It's going to refract. Sorry, that's probably going to bend towards the normal. That's pretty hard to see, isn't it? Okay, so it's going to refract towards normal. It's going to come back up, and it's also going to reflect. So we've got the original. This is the original reflected light, and then we have the refracted and reflected light. So it's sort of gone a little bit more distance, and it's the combination of both of those that cause the original red light to interfere with the other red light. Okay, now let's move on to learning objective number, I didn't know how to count, that's supposed to be learning objective number 2. Okay, so comment on the conditions for change of phase upon reflection at an interface. So essentially, it's this part down here that I've taken note of, is that light waves originating from a lower refractive index region. Okay, so it has to come from something like air usually, and then it undergoes a phase change of 180 degrees when it strikes the surface of the boundary. Now, the diagram that I'm drawing is more clearly, it's easier to see in terms of some additional things that I'm going to also illustrate on here as well. But most of this can actually work when the waves are completely perpendicular. Oh, I shouldn't have, that was supposed to erase that. So it actually works quite well when the light is perpendicular. So again, assume we have the sun here. So we have our happy sun, and it's giving off light. So I'm going to just use a darker color because it's easier to see. That light is nearly, or for our purposes, we just say it is perpendicular when it strikes the surface, okay? And when that happens, this makes it a little bit easier to see. It's going to cause a phase change when we have air, which has a refractive index of 1, and oil is about, I think it's about 1.5 or so. So what's going to happen is that it's going to come, and then it's going to rebound. It's going to rebound in the same area, but I'm going to draw it over here. It's going to rebound in the opposite direction like that. Okay, so really it's doing something like this, right? It's here, right? It's traveling further and further down, right? It's further and further down, and then eventually it's going to begin reflecting. Okay, so it'll be down here. Oops, I'm going to draw. Then it'll start to reflect on the other side, okay? Whereas the original, let me just maybe use a different color like green. So green is sort of the original, was on this side, okay? And then let's use maybe red is actually the reflected one, okay? And it travels along the same path, but it's flipped around, okay? So it undergoes a phase change of 180 degrees. Another way to also consider this is that again, 180 degrees, if you think about the unit circle, is 0, 90 degrees, 180 degrees. You can also consider that pi. So it's traveled pi in terms of our distance. Okay, let's continue. So learning objective number 3, we're going to look at thin film interference first, and then we'll look at some of the problems and how to solve that all together, okay? So let's get right into it. So first off, in terms of thin film interference, um, so again, we have our original ray that's coming in, and it's going to refract in oil. So this is easier to understand to draw it at an angle, but again, it's sort of coming straight down and straight up as we explained, but it's really hard to see it refracting, okay? So this is done for the purposes of illustrating that it may refract a little bit, okay? And then it's going to reflect off of this other surface, okay? But again, all of this is more or less happening straight up and down like that, okay? But again, it's difficult to see. So this is going to then refract away from the normal, like that, okay? And then the original one, I'm going to use maybe a different color for the original. So this is everything that's the original. I'm going to use red just to overdraw that. That's the original, okay? And the original is also going to reflect. And then the one that was refracted, I'm going to do in blue. Actually, I already got blue as water, so I'm going to use green. Green. So it's going to go down. It's going to go up. Okay, this is the reflected ray from refraction. Okay, so it's the combination of these two reflected rays. Whoops. It's the combination of these two reflected rays, right, added together that causes either a constructive or destructive interference. And something else to note here is that the refracted ray, you might notice that I've identified a certain distance in our oil. It also travels a little bit of extra distance, and we're going to see this in our formula represented as 2D, right? It goes down, that's 1D. It goes up again, that's another D. Okay, so that's why we're going to have 2D in our formula there. Okay, so this is sort of just in words why interference happens in thin film. So first off, we need two rays of light emerging from the surface of the oil or the thin film, whatever it happens to be. One of the ray has to be reflected at the surface. So I think in my previous diagram, I made that red. Okay, so that's the reflected one. And then it undergoes a phase change. And this phase change is either, you can describe that as pi, 180 degrees, or it could be, you could say it's inverted. And it has to come from a lower index into a higher refractive index region. The second ray will travel through the oil, and the ray has an optical distance of 2D n. N is the refractive index. And so they're doing a funny little thing where they, rather than talking about it slowing down and speeding up, it's just saying that it's traveling a little bit of extra distance through a refractive index that will be either given to you or you'll be asked to calculate it. Very similar to like refraction calculations that you've done in the past. And then, of course, lastly, the rays interfere, okay? So when whole numbers appear, it's destructive interference. And when half number, in terms of a wavelength, appears, they interfere constructively. Now, this seems a little bit counterintuitively because it's always been that when they're half a wavelength apart, this is a little bit different because if you recall, when the ray touched the surface, it undergoes a half phase change. So essentially what's happened is that if this was the original wave and this is the other one, right? So that's the inverted. Essentially, it's done a half a wavelength shift like that, right? And so because of that, it ends up being that whole numbers, it ends up being that whole numbers destruct and half values construct instead. Okay, so if you're wondering like what's going on, how come this is kind of backwards? It's because of that half phase change that happened. Okay, so in terms of solving problems, we've got two formulas: destructive whole numbers, constructive half numbers, okay? So last little bit, let's just finish off this calculation here is we got monochromatic light of 600 nanometers. I'm going to do this in gray. So that's a key piece of information. Shines on the surface of a bubble. Thickness of the film is 3.1 micrometers. Identify the type of interference observed if the refractive index N of the bubble is 1.5. Okay, so first off, I like to just sort of lay everything out. 600 nanometers. This is the thickness of the film, which is D, is 3.1 micrometers. And then we have N is 1.5, okay? And sometimes I just like to redo this as 600 times 10 to the power of negative 9, 3.1 times 10 to the negative 6. Okay, and then so let's do our substitution. So first off, we're trying to solve for, identify the type of interference. So we're actually trying to solve for x. So let's rearrange our formula, 2dn over lambda. Make our substitution 2 times our distance, 3.1 times 10 to the negative 6. 600 times 10 to the, oh, no. That's n. N is going to be 1.5. And that's divided by 600 times 10 to the negative 9. Okay, so once we get all of that, let me just do a quick little computation. 2 times 3. I'm going to cheat here. 1, 2, 3, 4, 5, and 1.5. We're going to divide by 600. That's the 600, and then 10 to the power of negative 9. And so that's going to give us 15.5. Okay, and so when you look at that, when you see 0.5, and you look back up on our little chart there, that's going to be constructive interference because of that 0.5. Okay, guys, that's the end of our video. Please check out some of the questions in your textbook and that things that I've assigned on Cognigy. We'll see you guys back next time, and we are going to head into chapter 9.4. See you guys next week.